Hello, everyone. My name is Oliver, and I'm one of the developers of the finite element method in the Wolfram language. And I'm trying to give you a little bit of an overview of what we've done in version 12. Yeah, so let's get right to it. So the finite element method is a method to discretize partial differential equations. And we've added first parts of it in version 10, then we added some more in version 11, and now in version 12, we added even more features. Previously, the finite element method was used to solve time-independent and time-dependent partial differential equations on arbitrary shaped regions. We had NDSolve to do is the workhorse basically to do these type of equations. We've added ND eigensystem to do eigensystem analysis. Parametric NDSolve is there to do parametric studies. In version 12, we now added nonlinear finite elements, and that means that in the time-independent and in the time-dependent case, the partial differential equations you can solve can now be nonlinear. So with this addition, the solvers are kind of feature complete in the sense that all major analysis types in the finite element world can now be done. We have linear, stationary, nonlinear, harmonic or ND eigensystem frequency-based analysis, and parametric analysis. So if you have a nonlinear partial differential equation, you'd also need boundary conditions, and these can be then solved over arbitrarily shaped regions. Just as a small side note, so NDSolve could solve nonlinear equations before version 12, of course, but those were done on rectangular regions by using the tensor product grid method, which is a finite difference related method. So now version 12 is a big step forward because now the geometry can be arbitrarily shaped. So what we have here is the marketing page of the nonlinear finite elements, and I want to take some time to walk you through the different parts of that and to show you what type of functionality we've added and what you can expect to do with that. So first, there's a bit of a summary that basically similar to what I've already mentioned. We have support for stationary nonlinear partial differential equations over regions. That means concretely that the coefficients of a partial differential equation can now depend on space and time and the dependent variable itself. That's what makes the problem nonlinear. The coefficients can also depend on the derivative of the dependent variable, and we're going to see some examples about that in a minute or two. This works for real and complex valued PDEs, so complex valued PDEs can also be nonlinear now. Concerning the boundary conditions, we have a nonlinear generalized Neumann boundary condition. That's typically used in something where you have a radiation boundary condition that has, for example, a temperature to the power of 4 or something like that, and we're going to see an example of that too. We can solve the time-dependent nonlinear PDEs over regions, and as is customary for NDSolve, these time-dependent problems, they use an automatic time-stepping technique. So it's not a fixed step method, but NDSolve will automatically adjust to find the right time step to time degrade your nonlinear problem. Like it did exactly the way it did for the tensor product grid method, but now for the nonlinear finite elements as well. You can formulate coupled nonlinear PDEs, so it's not restricted to a single PDE. You can have multiple nonlinear PDEs coupled together for multiphysics analysis, and that opens a whole slew of new domains that you can work with. For example, computational fluid dynamic problems are feasible now. Something else I want to discuss at the end is basically there's also a programming interface to this finite element method. So for people that are maybe a bit more advanced or would like to just use some components of this framework, they can program the finite element method. And another large contribution in this area is that FindRoot got a new Newton algorithm that's especially well suited for large-scale systems of equations. That's what the finite element method delivers, and that's why we needed a new algorithm that's tuned, or that's optimized for exactly this type of problems. Okay, so let's look at a few examples here. The first row of examples are basically somewhat contrived 1D ordinary differential equations, but the purpose of those is to show where the nonlinear coefficients can appear in partial differential equations. So this is a simple example where we have a nonlinear load term. And what you see here is we have a Laplacian type equals to the sine of u and some Dirichlet boundary condition. This is the way how you'd enter this in ND-solve. So there's nothing special or unusual about this. It's exactly the way as before in version 10 and 11. You specify the equation, with the only difference now that previous versions would complain about this term, and now it just solves this equation. So we've set up the equation, set up some boundary conditions on both ends. Say the dependent variable is u, and x, the region goes from 0 to pi half. And then we find the solution, and we can plot and visualize the solution or do any other type of post-processing that we would like to do. Okay, the next example in that same row is a complex value PDE. So in this case, again, we have a Laplacian type component in the PDE, and we have I, the complex number, times u squared, which makes it a nonlinear problem equal to 10. Again, we set up some Dirichlet boundary conditions, and this looks pretty similar to the previous example, just that we've changed the values of the boundary conditions and the actual equation a bit. But the workflow is the same. You specify the differential equation, the boundary conditions, what the dependent variable is, and the specific region. And you can now visualize this. What's nice is in version 12, there is this real imaginary plot. So you can now actually plot both the real and the imaginary component of the solution in a single plot quite easily. Yeah, that was a bit harder previously. Okay, so next example in this category. So now we have a nonlinear diffusion term. So as previously we had this Laplace equation, now we have a diff grad where the coefficient is the dependent variable squared. So this is a nonlinear type of a diffusion problem. And that's set to 4. So that's just the equation I came up with. And the way you enter this is used by inactive diff and inactive grad. And the reason is you do not want this part to evaluate prematurely. So that's why inactive components are needed. You always need that if you have a nonlinear component in the diff, between the diff and the grad of the equation. One other thing to note here is that I've actually specified an initial seeding. So if you remember, Newton's method works by you giving it a starting value. It needs some kind of a starting value to get started. And typically that starting value, or what we've done is that in the nonlinear finite element stuff, the starting value is typically set to 0, and we try that. But in some cases, that's either not leading to the correct result, or you might find another route somewhere else. And in order to control a bit what or where the solution goes to, you can specify this initial seeding, and you just say u of x, the dependent variable, is this 1, so it just uses 1 in this case instead of the default 0, and finds a solution. This expression here on the right hand side can be any expression. You can have a function, so you can have an old value or something like that. Maybe that's a good point actually to mention. So if you have a very nonlinear problem that's highly nonlinear, what and NDSolve can't directly find a solution to that. So one thing you can do is try to find a solution to a less nonlinear problem and use that as an initial seeding for the higher nonlinear problem. That's a common approach to solve extremely nonlinear problems. So, and that's done with this option, initial seedings. Okay. So as I mentioned earlier, we can also have nonlinear derivatives. So in this case, in this example, we have again like a diffusion type of term. And now we have 4 times the dependent times the derivative of the dependent. This again is a nonlinear term. And NDSolve can now also handle these type of terms. Again, so the equation is set up, boundary conditions specified, dependent variable, the region, and again, in this case, I used a different initial seeding. And then plotting works just as it did work previously. It's not nothing new. All right, so that was the first row of basic examples, just to show a bit where the nonlinear components can come up, and to give a slide, to give a little bit of a feeling of how it works. So the second row of examples is a bit more mathy physics oriented. And here in this example, so the first example shows how you can interactively solve nonlinear PDEs. Yeah, let's right away look at that. What we're doing here is we try to find the minimal surface area over a unit disk which has sinusoidal values on the boundary. And the equation that models this is given here. So we have diff 1 over square root of 1 plus the absolute value of the derivative of u squared. I specified this here in this equation. I've rewritten it a little bit. And then I've given boundary conditions. I solve the equation, and I visualize the solution here. So that's the minimal surface for the disk with these boundary conditions. One thing you can do is you can actually also solve this interactively. So to put this a bit in perspective, this is not going to work for super complicated coupled 3D nonlinear PDEs. But for simple nonlinear PDEs, you can interactively solve this. And then by moving a slider, so actually there's an animation here. So when I move the slider, you actually see how the solution forms while I interact with this nonlinear PDE. I think this is Mathematica is the only software that can do that, to interactively solve nonlinear PDEs to some degree, I must say. Okay, let's look at another example. So this example, the radiation boundary condition is I also mentioned that earlier a bit. So this is the nonlinear boundary condition. And in this case, we're talking about a nonlinear generalized Neumann boundary condition, and maybe it's best to quickly just look at that. So here's an equation that's actually linear, but it has this nonlinear Neumann value, so t to the power of 4, and that's something that's typically used when you want to model radiation. So that's something you can solve now. Right, so this is the solution. I've applied this. Okay, let's quickly scroll back here. So this part is applied at this upper part here, this semicircle, and yeah, that's the solution then to this PDE. Okay, here is a more of another application type of example. So this is from magnetostatics. So what we want to model here in this case is an electric motor. And this motor has a stator and a rotator and has some coils. And typically, we want what you have is you have the material data from these materials that are used in the motor. So these are typically the field strengths of the H and the B field, and they're related through the permeability. This data is something you typically find in material data sheets you get from a vendor of your material. And the first thing you do is you need to generate some kind of a fit from this data. So I've used this data, and what we see here on the x-axis is the B field, and on the y-axis the B field versus the H field. That's the fit I've used for this example. And let me see. Did I actually? No. Okay, the equation is coming just now. Just to show the setup of this specific geometry is, so this is the rotor. Here we have the stator. In orange, pink, and yellow we have coils. And what we're going to do is, so we're going to have a high current, a positive current through these coils, a negative current through these coils, and the pink ones are not going to have a current, and that's going to induce a field in the motor. So the equation that models this is a nonlinear Poisson type of equation, and it's 1 over the permeability, and the permeability is dependent on space and the derivative of the dependent variable. It's dependent on space because in various areas of this geometry, the permeability has different values, and we're going to see that just now. Right. So to model this, I've used the B2 norm, and I've used the first derivative in the y variable plus the first derivative in the x variable squared, and I've added some machine epsilon, and that's just because I'm going to be dividing by 1 over that. And in case this part becomes 0, if there's no field, we're going to be in trouble if we don't add the machine epsilon, just a small number to make it not go to infinity at that point. So the next thing here is this piecewise. So that means, let me scroll back a bit to this area here. So this mesh that we're using has markers. So specific regions are tagged with markers, and they allow me to use different materials if the solver is in a specific area. So if the element marker is 2 or 3, I think that's the numbers for these two, for the rotor and the stator, then a specific value is used, and in the other components, another value is used. That's why we have this piecewise. So if it's in 2 different regions of the geometry, then use this fit that we've just generated, and in all other cases, use this number. And the same we do for the load. So that's the coils. So in one coil, we have a positive current flowing, and in another coil, we have a negative current flowing. So that's the setup of this problem. We call ND-solve with the boundary condition again, and that's then the solution. So this is the visualization of the magnetic field within that motor. Okay, so that's that example. Here, the next example, a Sine-Gordon type equation, that's more of a mathy physics type of equation. And what I've done here is I've just used a coupled stationary nonlinear Sine-Gordon equation. So we have U and V. So now the new thing now is that we have 2 dependent variables. So it's a coupled equation, first of all. And both U and V terms come up in both equations. So that's the equation. I've used a somewhat random polygon that I just could come up with and specify the equation here in this part, set up some boundary condition again on the entire boundary, let ND-solve do its work. And this is the solution of both solutions plotted on top of each other. So that's just another example. Okay, so we have a couple of questions. Yeah. So the first question is, what is the level of interactivity? So the level of interactivity for the 2D slider example I've showed. I mean, it depends to some degree on the hardware that you have. So if you have lots of CPU power and RAM, you can do more than if you have a small laptop or something, a small device, a small computer. But as I said, I don't think you're going to be able to do interactive Navier-Stokes in 3D. That's not going to work. But for smaller problems, you can give it a try. It's very hard to say a specific number. So if it's a single PDE, your chances are better, and if it's in 2D, it's probably better. Yeah, that's kind of what I can say about that. You'd have to try to see whether it works for your specific application. So because I mean, you have to think about it. So the nonlinear solver has to solve linear problems over and over again to actually get to this nonlinear solution, and they do take time. So even though I've tried to optimize this as much as I can, having a real interactivity is very hard, but it works for some smaller type of problems. So give it a try. So there's a second question about whether this can be the finite element framework can be used for as I understand it, for lesser dimensions. So for example, if you like to solve a nonlinear PDE over a surface, that's currently not possible. Okay. So let's continue. But if there's more questions, please don't hesitate. I'll try to answer as good as I can. Oh, there's another question. Okay. So the question was whether it's possible to visualize the mesh and how much control you have over the coarsity and density of the mesh. So the answer to the first question is yes, you can visualize the mesh, and there's an entire tutorial about just doing that. If you happen to have Mathematica available, or even you could look on it online about the element mesh visualization. That's going to show you how to visualize the mesh. For coarsity and granularity, there's two things you can do. You can either just specify a specific parameter, say max cell measure, that specifies how large the cells are allowed to be. And that's going to give you a certain refinement. Or you can actually write an entire function that actually takes out a specific part of a region, for example, and refines that region in that specific area. And the keyword there to look for is the mesh refinement function. So both are possible. Okay. Right. So up until now, we've only seen time-independent equations. So now we're going to look at some transient nonlinear equations. So the first one here is a transient nonlinear wave equation. That's a wave equation Stephen came up a few years back. And so this is the equation. You have du dt squared. So it's a wave equation type of equation, a Laplacian type of term, and then this is the nonlinear term that we're trying to solve. So that's here. It is set up. Now, because it's a time-dependent problem, additionally to the boundary conditions, we need to specify initial conditions. And because it's a wave equation, we also need to specify the derivative of the initial condition. So these two are specified here. And the Dirichlet condition is set on both sides is just 0. We use NDSolve to solve the problem, and here's the result. And that's an example that you could have done previously with the tensor product grid method, because this is a rectangular geometry. But you can now also do this with the finite element method. So there is some overlap between some of the methods. So yeah, right. Next example is a Gray-Scott example, transient Gray-Scott model. So these are used in biology. For example, if you have a Petri dish and you grow bacteria on them, that's how the bacterial growth could be modeled. So this is the equation. So this is a first order time derivative. Again, we have some Laplace, some diff grad type of terms. And here, this second part has the nonlinear term, actually. U and V are the two variables. So this is a time-dependent coupled nonlinear problem. So, I mean, the examples in the future are going to get larger and larger. And I don't think it's worthwhile spending too much time on looking exactly at the equations, because things are going to get a bit complicated. But basically, all the pages have the actual equation that's used and modeled on top of it. And you can take it from there, I think. Right, so again, initial conditions for both dependent variables, Dirichlet conditions, and then we've used this NDSolve command. And coming back to the previous question, so in this case, I've used a finer mesh than what's the default mesh. So that's how that would look like. So I said the PDE discretization uses the method of lines, which is a time integrator. And for the spatial discretization, I use the finite element method, and I've used the mesh options and say that the mesh should have the maximum cell size of 0.03 units. Okay, so, and this is then what that looks like. So this is a growth, that's what the Gray-Scott type of equations can model. Okay, so let's see what else we have. Okay, this is a transient Landau-Ginzburg model. And what I've done in this case is I've split it in real and imaginary part. To be very frank with you, I don't remember why I did that. In principle, this should work as a complex valued equation. I honestly, I can't remember why I split it, but that's what I did, and here you are. So it's basically now two equations in U and V, and this comes up if I know correctly in the theory of superconductivity. So that's where that's used. Again, setting up the equation, initial conditions, some boundary conditions, and call NDSolve, and here's a solution with that plot. Again, this is an example where the tensor product grid method could also have been used because it's a rectangular region. Okay, so here we have a transient nonlinear heat equation. And let me see. Oh, right. Oh, okay. So I didn't see that U here. So this is so we have a div U and an anisotropic heat material parameter. So it's one on the diagonal, and on the off diagonals is a half. Just to show that something like this is also possible. Right, we specify a region. We set up the PDE. It's a first order time derivative, and have a Neumann value. That's linear though. This is just the U. It's not squared or anything like that. So it's a linear Neumann value in this case. We have some boundary conditions, initial conditions, find the solution with NDSolve. And here's a contour plot of the solution at a specific point in time. Here we have another one in 3D. And right, so because we previously, so you don't see it in, you don't see it in the example itself, but in the thumbnail for the example, you actually see the mesh below. And this mesh, that's the actual mesh that's been used, and that's actually also the visualization, this how this mesh is visualized. So that's, at least there's a small example of doing this. Okay, there's a question. Yes, sorry, the question was whether heat sources can be included. Yes, heat sources can be included. That's not a problem. Okay, so we've done time-dependent problems. The next row is a theme row, so it's basically computational fluid dynamics. And the first example is solving a time-independent Navier-Stokes equation. So we've got some viscosity. U is vector valued, so it's the x and the y velocity, and we have a pressure P. And so this is actually, it's three equations: U, V, and the last equation P. For P, where P doesn't even appear, which makes it a bit tricky to solve. But yeah. And the application here is that we'd like to compute the fluid flow over a backward-facing step. That means, so on the left-hand side, we have an inflow, and that's the inflow profile that you're seeing here. And there's a step, and we'd like to know what the fluid flow looks like in this specific geometry. So this is the inflow profile. That's exactly what you're seeing here. And the boundary conditions say that in the beginning, the inflow is just in the x direction. There's no flow direction in the y direction. It's set to 0. At the outflow, we set the pressure to 0, just a reference pressure. That's at this end then. And all other boundaries are walls. So we set the u, the x and the y velocity, the x direction and y direction velocity to 0. So that's a wall boundary condition. We've grouped them up here together. We set up the Navier-Stokes equation, and then we've used ND-solve with some specific material parameters: density 1.3, viscosity to the power of -5. Right. So one thing that might be a bit strange is this interpolation order. It means U and V are interpolated second order, while P is only interpolated first order. Typically, if you solve fluid flow type of problems, this is a way to get a stable solution. That means that the velocities are interpolated or computed in a higher order than the pressure. Right, so that's just our way of specifying this. It's a standard procedure for fluid dynamics with the finite element method. Here's a stream plot. That's the plot on the of the velocity profile. Here we have a density plot of the average velocity field. That's what that looks like. And then there's a plot on the pressure within this this geometry. All right. So the next thing is, after we've done the time independent, of course, we'd like to do the time dependent Navier-Stokes equation. So same equation as before, just we now have added the du dt term. And note again, so this last equation doesn't even have a time derivative, so it makes it again a bit more complicated, but you can compute something like this now. So the application now, this is a standard test problem. So we have a cylinder in a geometry, and that cylinder is just slightly unsymmetric, so it's slightly higher than the symmetry axis. We have an inflow profile, and the right-hand side is the outflow, and all other boundaries are considered walls. This is how we set up the equation. Now we have a time derivative on t term, and the rest is the same as what we had previously. Right. So what we do now is we write ourselves a small function that slowly ramps up this this inflow velocity. That's this. And the inflow is then we have the x velocity is this inflow profile, and the y velocity is 0. Similar to what we had in the previous example, just that we're slowly ramping this up. This inflow is now slowly ramped up. Again, on the right-hand side is the outlet. Its pressure is set to 0, and all other boundaries are walls. Yeah, there's a question. The question was how I can enter a non-evaluating nebula. So if you use so basically this is done with inactive div. So you'd look it up in the help browser, and there's going to be examples, or even the NDSolve reference page probably also has examples where you can find that. So inactive div and inactive grad is what you're looking for, and the keyword is inactive, and that's wrapped around the div and the grad. Right. Okay. Boundary conditions, right? Initial conditions, everything is at rest, is at 0, and then we time integrate this. Again, we use the stabilization technique. We use a finer than the default grid, and we have an evaluation monitor in this case. And what that does is that monitors the progress of the time integration. So the time integration in this case takes 152 seconds. And when you run this, you can actually see this progress when it computes the solution. So that's useful. I mean, sometimes nonlinear time-dependent problems can take a long time to run, and you'd like to know whether it's still making progress, whether the solver is making progress, or whether it's somewhere in a bad zone where it's just hanging around and not really doing anything anymore. So that's a way to monitor something like that. And after we've computed the solution, basically the post-processing, in this case, the visualization is done. So here we have a plot of the vorticity, and this is the visualization of the common vortex street that's happening after the cylinder because it's slightly off symmetric. Okay, so nonlinear time-dependent Navier-Stokes. Right. So we haven't had a 3D example, so let's go full. And this is the 3D transient fluid flow problem. So same thing as before, just in 3D. So this is now 3 equations, is U, V, and W, but the rest pretty much remains the same. This is just a geometry I constructed. It's a ball and 2 spheres connected to it. And here you actually see the first time, this is a call to one of the nonlinear, to the finite element framework to generate the mesh. So yeah, you can also do that if you like to do that. Here's the dependent variables U, V, and W. This is the equation. As I said, the equations become longer, more terms, but it's in essence, it's the same as in the examples we've seen previously. So again, we use this type of a ramp function. The inflow profile on the top cylinder is like that. It's just, this is the inverted plot. And this is the boundary condition at the inflow. Just uses the minus velocity profile on the z-axis. The outflow is on the other cylinder. It's again, we set the pressure to 0, and everything else is set as a wall. Yeah, initial conditions are everything is at rest initially. We solve this in 3D. It takes 600 seconds to solve. This is done on my laptop, and it's not a particularly powerful machine. But I mean, yeah, if you have a large machine, it's going to be a bit faster, I guess. Yeah, and it used 3.5 gigabyte of memory to solve this problem. We can now look at the minimum and the maximum pressure, what the pressure difference between the inlet and the outlet is. Here we have, let me see what I have. The maximum and minimum velocity, right? And here is a visualization of the vector field of the velocity flow within this, this geometry that we've created. Okay. Next example in this area is, so We're going back to 2D now, but we're going to add more equations. So what we're doing now is energy transport. So we couple the Navier-Stokes equation with the heat equation. So again, Navier-Stokes equation, first part, heat equation. And the heat equation gets the velocity field from the Navier-Stokes equation. That's where it's coupled. And the Navier-Stokes equation also gets the temperature from the heat equation. This approximate. So what I'm trying to do is, so we have this geometry, and on the left-hand side, we'll slightly heat this this side and slightly cool this other side. So due to the temperature difference, a fluid flow will be induced in this object, and we're trying to compute that and visualize that. So that's the geometry. So this time, I didn't mention this before, but in this time, I've used a Reynolds averaged type of version of the Navier-Stokes equation. Previously, we just directly entered the parameters into the Navier-Stokes equation. There's no particular reason why I do this here. I just wanted to show that you can also do that. It's just a different way to set up the Navier-Stokes equation, just to show that this is also possible. Right, so boundary conditions, everything else is a wall. So we have a heating and everything else is wall. And initial condition, everything is at rest in the beginning. And so this is, we call ND solve. We wash it. This is in 53 seconds. It's done. And right, so this is a temperature. Oh, sorry, this is the pressure distribution. Let me see. I thought I had a video here somewhere. Yeah, that's the one that's interesting, actually. So now you see, so while this is heated on the left-hand side, you see that slowly a fluid flow is forming. Now, the interesting thing is, if you actually change the geometry to this, so this is just inverting this here, the fluid flow profile is completely different. Yep, have a look and try it out and see what it looks like. So just something for you to do if you want to. Okay, so that's the next the fluid flow row. The last row is a bit of miscellaneous, so different items and stuff that we're working on currently, and some of maybe lower level functionality. Right. So the first thing I'd like to talk about is learn modeling acoustics with PDEs. So what we're trying to do now is we're trying to come up with tutorials, monographs that cover a specific subject area and start to drill down a bit deeper into those areas and how you can use ND-solve and the finite element method in these specific fields. And the first field we've looked at is acoustics. The reason we've chosen acoustics is it's a single equation, it's linear, so we can. For us, it's also a learning process how to write these tutorials and these models. And that's why we've chosen acoustics as a first go. And if you look in the help browser and just type in acoustics or something, acoustics PDE or something like that, the browser will take you to two tutorials. One is the acoustics in the time domain, and the other one is acoustics in the frequency domain, where we drilled down into these areas and shown specific equations, what boundary conditions come up in these areas, how to use the boundary conditions we have in the system to model these acoustic boundary conditions and things like that. So if you are interested in acoustic, this is definitely interesting for you. But even if you're not so much interested in acoustics and have a specific other field that you're interested in, write me, let me know about that. And let me know if you think this type of tutorial is useful for you, but for learning specific areas. So the example we've chosen here, and that's just a simple example. That's not the tutorial looks a bit different. You can look that up in the help browser later. So we have two small pipes here, and there is acoustic pressure sources on both ends, and we're modeling this. So I don't want to go too much into detail into this. and there's a refraction pattern that actually can be reproduced with this. So that's something we've worked on. So modeling with specific in specific application areas. That's another thing we've been working on. Another thing I'd like to draw your attention to is, so Wolfram Research has a GitHub repo, and on that GitHub repo, there is something called FEM add-ons. These FEM add-ons contain various things. So for one, it has programming code that customers contributed, and they couldn't go into the kernel for one reason or another, or we didn't want them in the kernel for one reason or another. So it's a collection of customer contributed extensions to the finite element method. The other thing it has is application examples from customers. So if someone is modeling something and they feel they like to contribute that, they're more than welcome to do so. And we'll just put these notebooks in one single place. So if you are working with a finite element method, that's a place where you can find additional material. And the page has instructions on how to install that and everything. Right. To give you a little bit of an overview of what is there. So, for example, you can have structured meshes can be generated. You can generate structured meshes in 3D if that's interesting for you. You can convert triangle-based meshes into quadrilateral meshes. That's another function that's there. There's a function called distmesh. It's a famous mesh generator that produces extremely high quality meshes. You can use that, very smooth meshes, if you want to use that. Oh, here's a particular gem that I think nobody knows about this, but so there's a domain decomposition solver. That means you can run ndsolve on a cluster of computers. So if you have a large cluster, you can use domain decomposition ndsolve and solve equations on that cluster by specifying different kernels. So in this example, we've just used 2 kernels. But if you have a cluster with, I don't know, 40 kernels, you can just use 40 kernels. This is useful not in the case when you have a multi-core machine, then Mathematica or ndsolve as such is already quite optimized. But if you have different computers that you'd like to connect to, so then the domain decomposition ndsolve is a way to go, probably, or to try at least to solve a particular problem. What that does is basically it takes a particular mesh and splits that mesh into particular domains and subregions, computes the solution on the subregion, and propagates the solution to the respective other boundary conditions and tries to stitch together the solution from the different components. So that's another functionality that's available in this finite element add-ons. Yeah, I think that's all I mentioned. You can check out the GitHub site, and there's more information there for you if you want to. The programmatic API to the finite element method. So the finite element method, as it's implemented, has a lot of examples on the ndsolve level, but all lower level functions that are used within the kernel are fully documented. They're pretty fully documented. Maybe some option or another is not documented, but the vast majority of stuff is documented. What we've added now in this version is that if you want to, for example, write your own linear solver because you want to experiment with that, because you have an idea for a better linear solver, you can do that and then hook that back into ndsolve to compute. Oh yeah, there's a question. Oh, the question was whether this will work with a lightweight grid Mathematica. Honestly, that's a very good question. And I haven't tried. I didn't think about this. I should have tried this, but I haven't. So I don't know. Probably the best thing is to try to contact technical support about that, and they'll be able to reach me, and we can try to figure out whether this works. It's an obvious solution, but I didn't think about that. So maybe that's a good thing to try, actually. So if you'd be kind enough to contact me via support, we can try to figure out whether this works. I don't know right now. No. Okay, back to the linear solver. So this is just a very simple linear solver we've written based on linear solve just to show that this is working. And then again, we use this minimal surface problem we've seen earlier. And what you can now do is you can specify the equations as you've used to, but now you can also specify PDE discretizations, finite element, PDE solver options, the linear solver, and then you can plug in your own linear solver that you have written. So that's type of the stuff you can do with the API. But if you look in the documentation for the lower level function, there's a lot of documentation on those too. Actually, if you're really interested, the code for the nonlinear solver, how the nonlinear solver works, is in the documentation. So you can look that up and try to follow what I've been doing there. And if you find bugs, let me know so that I can fix them. Yeah. Right. So that's same thing there. Right. So the last thing I have here is I mentioned this earlier that we've added a new method to findRoot. So findRoot's default method is a Newton method, but for the finite element method, that's not that applicable because it doesn't care how often it has to use to evaluate the Jacobian and things like that. But in the finite element world, evaluating the Jacobian is very expensive, and we absolutely have to minimize the evaluations of the Jacobian. And the affine covariant Newton algorithm is something that tries to do that as best as it can. Here's a simple example. So there's a nonlinear equation, u to the power of 3, Laplacian type of term. And I've just simply discretized this by hand with the finite difference method because this is not really important here. But the system matrix here is 1,000 by 1,000, and I can also easily compute the Jacobian of this example problem. I've chosen a starting value, a constant of zeros, constant array of zeros. So and now we use findRoot with the default method, and we see that it uses 3 steps, 4 function evaluations, and 3 Jacobian evaluations. Now, with the new method, the method affine covariant Newton, it uses 5 steps, 6 function evaluations, but only 1 Jacobian evaluation. And the fact that it uses more steps and more function evaluations is, for the finite element method, almost irrelevant. The fact that it uses only 1 Jacobian evaluation, it's really important for the finite element method because it's so much more efficient to solve the nonlinear problems then. This algorithm also has something called Broyden updates. So it actually understands how good the Jacobian is an approximation to the system, and it tries to reuse an old Jacobian as long as it can. So it keeps track of how good it is. And if it finds, the old Jacobian I'm using is no longer applicable, then it computes a new one. But if it can use the outdated Jacobian, it will use it for as long as it can, and thus try to again minimize the amount or the number of times the Jacobian has to be set up and evaluated. So that's that. Yeah, and there's more details in the documentation. So all the examples I've shown are in the documentation, and they have more text to it, explaining a bit more the physics and stuff behind it. So yeah, that's you can find more information in the documentation, I think. Right. So that's pretty much what I had to say. So are there other questions maybe? No, doesn't seem to be the case. So then I'll thank you, and thank you for your attention. And I'm going to wrap up here. And yeah, so if you're using the finite element method and want to share something, send me a line. Send it to tech support. They'll find me. And yeah, have fun using the finite element method. Yeah. All right. That's it then. Thank you. Bye-bye.